Now this is an electronic lamp ballast from a commercial fixture. This is meant to run 4 lamps, as we can see here. And the cool thing about these electronic ones versus the magnetic lamp ballast is that they start up really fast. I think, in my opinion, they seem to be a little bit brighter than the magnetic ones. And the bulbs, I think, last a lot longer with these electronic ones because they're not sitting there heating up the filaments on the ends to, you know, get them to ignite or anything. And these are operating the lamps at like 600 volts, I believe, on these. So the filaments on the ends of these, if you can tell right there, all the filaments are connected in parallel, basically. So each filament basically is acting as an electrode. So this came out of a commercial fixture, but this one's dead. And so we're going to open it up and take a look inside and see if we can figure out why this one has failed. And there's really not much to opening these up. There's a few little tabs right here on the ends that need to be lifted up, and that's probably the most difficult part of taking these things apart. Although I have it sitting here on this tray because you'll see why in a second here. And also, I don't know if you've noticed it, but it looks a little like there's a moisture on the outside of it, and that's because I just took it out of the freezer, and there's kind of a reason for that as well that I'm hoping will actually help with digging out the contents that are inside of this, but we'll see. So let's get to it here. Let's start lifting up these tabs here, and even though these tabs are like really thin, they're actually really hard, but this plier here is making a pretty quick work out of it, so this should be fairly easy. Relatively easy. I'm not like gonna repair this or anything, so I'm really not worried about trying to keep everything like completely intact. So I will undo all these tabs and we'll remove the... Oh, that was actually a little bit easier than I was thinking it would be. So here's the back cover. This comes off, and as you can see, everything inside is potted in tar, which is really annoying. So that's why I have this tray here, so we can at least collect all the tar that falls out of it. Take the remainder of this back cover off here. Alright, we'll set that aside. So, what can we see so far? Yeah, that's 2 electrolytic caps right there. We're also going to have some transformers and some inductors and stuff hidden underneath these things. So that's kind of why I froze this. I wanted to hopefully make the tar as brittle as possible. You can see right here in this kind of protective layer that they have in the back there, there's some tar there. It cracks fairly easily because it's cold and crispy, so I'm hoping that will help with digging out the board in there. I should probably get a little bit more light here. Alright, so there's really not much holding this inside of there. It's pretty much just going to be the friction from the tar. So the sides here, I'm trying to loosen it up. There's these little sort of grommet things right here where the wires come out of. This is the input right here, so we have our neutral and our live coming in. These 2 yellow ones are for one side of the lamps. Each of these wires feeds 2 lamps, and then we have 4 individual wires over here, 1 for each lamp. So let's see if we can get this to pop out. It feels like it's loosening up. Probably going to take a little bit of work. I think these are going to have to come out here. They have these sort of like little tabs on the side right there, so I'm going to have to pop this out. If I move this out of the way here. There we go. It's gone. It's gone. There it goes. Alright. So that one is free, so this side should be relatively free. The other side has 2 of these. So let's move these onto the side. We'll pop this off here. This should just break off. If I twist it enough, there we go. Okay. Now these should also slide off. They've got these little grommets on there to protect the wires from like rubbing on the that sheet metal and potentially causing shorts. If we look over, oh yeah, it's actually right here. On this side, there is a green wire that's just kind of there on the corner, but that is actually a grounding wire, and it's sort of just kind of pinched in between the layers of metal there, between the back cover and this top cover here, so that basically makes the whole thing grounded. So that's what that's doing there. And if I peel this away a bit, I might be able to loosen it up. Alright, this seems to be fairly free on this side now. There's one. And okay, this one's coming up. There it is. Okay, so this yellow wire, or these yellow wires that are right here, are not actually attached anywhere on this side of this ballast board. They actually run all the way across to the other side. Wow. Okay, see, you can see right there how it came out of this way, and then it just kind of crossed over to that side. Oh, it's very hard. But anyways, basically all the output circuitry is on this side of the board, and we're gonna see what's in there. I mean, I've already taken these apart, so I already know what's inside of these, but anybody that hasn't seen the inside of one of these and is kind of interested to know, I'll just kind of do it in steps here. I won't really spoil anything much. So I think this should come out here anytime now. Okay. So there is the top cover. So as you can see, it's just basically a tub of sheet metal. Set that aside. So the board itself is also protected in this protective paper stuff. It seems to be coated with something there, almost like it's laminated. And this is basically just an insulator, just to prevent any part of the bottom of the board here from shorting against the case. Not much to see there. I mean, that's all it is, just an insulator. So we can see everything potted in tar, and I'm hoping that it being frozen has made it brittle enough for me to maybe just twist it and have it crack. And oh, it's certainly cracking, so I think it kind of did help. Yeah, hopefully it'll just come off in chunks. At least that was my intention for freezing it. Yes, okay, look, we can start seeing components already. So these are caps right here at the input for like filtering and stuff. And let me see, I'm gonna do my best here to try not to break the board itself. But if it breaks, oh well. Here we go. We can start seeing our electrolytics right there, and stuff just kind of peeling off. So that's I think that's actually working out pretty well. Let's see if maybe we can pull these wires all the way out. It might help release some of this stuff in the middle here. Wow, I just got little tar pieces just flying all over the place. You can see I can bend the board quite a bit. So yeah, this board is basically like the whole length of this thing. And right here we can already start seeing some power components. That there looks like a TO220 package, and there's going to be another one right here. We can see that these things right here are like little heat sinks. There's a transformer or an inductor of some sort right there. You can see the core material. And let's see if maybe I can dig some of this out with a little screwdriver here. We're going on an excavation. We're seeing what stuff is hidden here in the tar. So I might have to just kind of chip away at this for a bit and then maybe have to come back. Let's see how much we can remove just by... Maybe if I hit it with the screwdriver or something, I can get a lot of this stuff to just kind of break off. Told you we were going on an excavation. Yeah, me tapping around like that probably did not help with this transformer getting loose there. Looks like I broke the plastic. So it still looks like it's still soldered. So I don't know, maybe it will work, maybe. I really don't know. Okay, they're chipping away at this for over an hour. It's been that long. I think we're just going to spray the more important looking components here with some brake cleaner, hoping that maybe it'll remove some of this tar here, and we can see what they are. Notably, this IC right here, this I'm pretty sure it's going to be either a transistor or a MOSFET, and then these other two right here, they're going to be transistors or MOSFETs, so we can see what those are. We can pretty much see what the rest of everything else is. Like these right here are just some diodes, like I already mentioned, for the input rectifier. All these caps would be, I think these are like safety caps. And this here's just going to be like a common mode choke for the input. Another cap right here. This one here is going to be our main this is, I believe, a transformer that is putting out like, I don't know, about maybe 300 something volts or something like that. I don't know. We'll take a better look at it. I don't remember exactly how these things are configured. I've seen them before, but I don't remember the exact details. So we'll take a look at that. The only thing that I've noticed that maybe looks like it might be an issue is down here. This resistor looks like it may be somewhat burnt, or I don't know if it's just the tar that's making it look that way, but no other resistor around here looks like this one does. So we'll see about that. We'll see if we'll check these devices, see if any of them are shorted. And yeah, I'm gonna get you in closer, just in general, to everything on the board here. We'll look at it up close and see how everything's just sort of wired up in here. But yeah, I also want to blast this area down here with the brake cleaner, see if maybe it helps remove some of this stuff. I don't know of any particular cleaner that's good at removing stuff like this, so I don't know if anybody knows. Maybe put it down in the comments or something. I hope I don't ever have to take apart anything like this that's covered in tar, because it's not so much of the fact that it's messy, it's just extremely annoying trying to get into the little crevices and everything, trying to get the stuff to chip off. It's just extremely tedious, and yeah, I hope I never have to do anything like that again. I mean, I'm only doing this here just for the sake of education, and so anybody that's been wondering what's inside of one of these things can see what's in it and maybe, you know, see how it works. So alright, let's give this a blast and see what good it does. Alright, so here we are actually outside on the outdoor workbench, because we're going to be spraying with this with brake cleaner and obviously, you know, well ventilated area and all that stuff. So let's see if this does us any good. Not really seeing much action here. I mean, it's getting a lot of the little loose chunks off, but it doesn't really seem to be like dissolving any of this stuff here, so maybe this isn't going to do much good. Well, that's kind of disappointing. Shoot. I was really hoping for more. I guess not. Let's see, what about the bottom? Nope. Dang it. Okay, so that didn't work, but I got some JBD-40 here, and it says it does clean tar. So we're going to soak it. Here, we're going to spray it and see if it does anything for us. And, are you kidding me? I think the nozzle clogged. That's lovely. Okay, there we go. Maybe we'll have to scrub it too. Give it a good time. Oh, dude! Well, we've got a bait here. Let's see if we can just do some cleaning. Whoa, actually that's helping out quite a bit. Hey, not bad. it's smearing the crap out of it, but maybe if it dissolves enough of this, we can just wash the rest off. This resistor down here that I thought was burnt, looks like it might actually not be. It's just kind of a dark color. But we will find out, I guess. Okay, I've got this sitting here in the ultrasonic bath. The water's pretty hot, and I'm going to sprinkle some of the cleaner stuff on top of it here. I'm going to turn it on, and we're going to watch some of that stuff, the tar, fly off of it here in a sec. Alright, ready and fire! It's not as drastic as I was hoping it would be. Man, nothing's working out. I mean, it's kind of working. You can see like the black cloud right there, just kind of haziness leaving the thing, but alright. Whatever this does, this is what we're going to have to settle with, because I don't want to invest a whole lot of time into this. I think I've already spent quite a bit trying to get this thing clean, and it's only kind of marginally working. Alright, let's see what we end up with here in a minute. I think that's about as clean as we're going to be able to get this thing. So, I mean, there's still quite a bit of like tar residue everywhere. You can see that there's still a little bit of moisture there from when I washed it, but we're not going to power this thing up. So whatever, no big deal. So now that we've got this one here kind of done with, let me show you a couple others that I've taken from some other ballasts. This one here, you can see the top doesn't really have much tar, although it does have tar, but it was mostly applied to the bottom there. I've kind of scraped off here. I was getting some stuff off, just, you know, kind of see what that was all about. So that one there, and then this one here has not been coated in tar at all, and as you can see, this one has quite a few surface mount parts on the bottom there, and actually it was pretty much similar to this one here, where there's quite a few surface mount devices, although the design's slightly different, but I mean it works pretty much the same. So if we put these all side by side here, we can see that there's really not that much difference to these. You can see right here that this one has the 20220 devices right here. They're insulated, and basically these would sit up against the case, and that's how the heat would be synced from those. There was another device here that's missing that I've removed. This one was basically all the power devices were just SMDs. You can see right there's a couple devices here. There was another one here, but that's been removed. So, well, let's look at this one up close now. Alright, so I had already finished recording this video, and you know, I was completely done with everything, and once I went back and kind of reviewed the footage, I really did not like the way it turned out. When I was going through and, you know, trying to figure out how everything in this inverter or this ballast works, I was making a lot of assumptions, and I realized that some of the stuff that I was saying I was kind of wrong on once I actually went back and looked at this with a little bit more detail. So what I decided to do is completely redo this, and I desoldered the transformers and inductors to make it a lot easier to be able to get in there and see what's going on. But not only that, I also took some time, which took me about like 2 hours, and I drew up a schematic of everything. And I think I could have done a little bit neater on this, but it had already taken me long enough to do it as was, so I didn't want to, you know, redraw everything. And where possible, I wrote down some values. There's some things that I couldn't really see, like the numbers on some of these diodes without like removing everything, so I didn't really bother with that, but I wrote down like a bunch of the resistor values. And some of these resistors are 4-band, and the way the bands are kind of printed on, it made it a little bit difficult to figure out which one was the beginning and which one was the end band, because it looks like they're pretty symmetrical. And like, say this one here starts with it's got red and a brown on one side, but they're like different tolerance resistors. So some of these are like 5% and some are, I don't know, they look like 1% or whatever. So some of these took a little bit of guessing, But after, you know, seeing how they were wired in, I was able to figure it out a little bit better. And it was a little bit difficult messing with or getting the values on some of these resistors right here, because that was around the time when I was having the probe problems with my meter. So that was one of the reasons why I wanted to get the leads working properly, is because this is when I found out that I had an issue. When I was measuring some of the resistors in here, that's when I was getting like a bunch of funky values on the meters. So that's why I needed something that was going to be a little bit, well, way more accurate than what I was getting with some with the bad leads. And also, I don't know if we're going to be able to get this thing working or not, because I still don't really know what the actual issue is. That was also the reason why I had gotten the kilowatts, so that we could check and see like how, if I can get this thing working, which I don't know if I can. So, you know, this might have been like a total waste of time. But if we could somehow get it working, you know, I wanted to plug it into the kilowatt and see what sorts of you know, power it draws, like from the wall, you know, like how much current and stuff. And yeah, so let's go through this with more information, and we can see how exactly it all kind of works. So really, this entire ballast board, basically, it's kind of works in like 3 sections, or there's like 3 parts to it. There's the input here, where it's kind of like filtering and rectification. And then after that, it becomes the power factor section, and I kind of wish I would have drawn this in like one block, but I wasn't exactly sure how everything was wired yet, and I was kind of adding stuff as I went. So basically, this whole area here is another block, and then we have this area down here, which is the output. And this is pretty much like self-contained. So if it wasn't for this being here, we would just have like a high voltage supply in this. And the output of this area here. So we'll start from the beginning and go through it, and until we get to the lamp output. So all the input stuff is it's pretty basic. We have our live input, we have our neutral, and that can be seen right here with our live and our neutral. And my fingers are orange because I had just peeled an orange not that long ago. So yeah, so that goes through this, and I didn't bother taking this one off because that was it's pretty easy to tell what's going on here. So here's all of our rectifiers. And that's these right here. And then we have some input. We have an input capacitor over here, and then we have another input here, or not an input, but a capacitor to earth ground. Oh, and another thing is that I also have like earth ground right here. In some of the other sections we have ground, but this one's actually like power ground, like inside the ballast. Those have nothing to do with earth ground. So as we can see, this ground here is not directly tied to earth ground. So that's only coupled through with this capacitor here. So this here is the negative rail of the ballast, and then we have our positive coming up here. We have a capacitor right here, which is would be this one right there, right before it goes to our first transformer right here. And at this point here, it's going to measure about 170 volts. And I think now that, you know, I've kind of understood and studied this a little better, we can actually go through it and kind of poke around and see what things, you know, kind of measure at or whatever. So at this point here, we should have about 170 volts. So that goes directly to the first transformer, and that's driven by this MOSFET that's down here. That's an 07N660C3, and that would be this little guy right here. That's the one that's doing the switching for that transformer. So that's going to boost our voltage, which is going to be rectified by this diode, which happens to be that one right there, that big one, and gets filtered by these 2 big capacitors right here, which happen to be these 2 right there. This transformer has 2 windings in it. It's got the first winding here, which is the one that's being switched, that does the boosting of the voltage. And then it's got another secondary winding, which goes through a diode to ground, which would be this ground right here. And then it goes through a resistor over to an input on the PFC chip right here, which happens to be labeled ZCD. So that one goes all the way down to here, which is pin 5 on that 8-pin chip. So that's basically like doing zero crossing like detection. I gotta look at the data sheet to be able to give you a little bit more detail on that. But that's where that's going. So this section here is just feeding straight into that pin right there, pin 5. The MOSFET itself, the gate, gets driven by the PFC chip over here, and it's got a diode and a resistor, a 100 ohm resistor right there in parallel. That goes directly into the gate, and the gate also has a 10K resistor tied directly to ground to, you know, keep this from, basically to keep this like clamped to ground. Or, well, I mean, it's got a pull down, but it's not clamped like directly to ground. So that way, you know, if anything happens over here, this stops switching, you know, then the MOSFET does nothing. This resistor right here happens to be a 0.47 ohm resistor, and this goes out. There's another trace that goes from this point here, which is CS, over to this pin right here on the PFC chip, which is a CS, so that's a current sense. So that one there is the one that's doing monitoring of the current of the boost circuit. So it's, I mean, it's really, there's really not a whole lot of like complicated stuff going on here. It's all pretty like point to point. There's nothing in between. So that there is all that pretty much has to do with boosting the voltage, because once it comes out of this point, then, you know, it just goes to the high voltage section. And I think at this point here, we're expecting to see about 360 volts after it's switched. And this is center tapped, but that goes off to the high voltage step up here for the lamp. So we're gonna look at that later. And so basically here at this point, let's just say we have this. So if we go back to the PFC chip down here, there's kind of a couple things going on that I noticed, and one of these might have something to do with why this doesn't work. Up here at this point where I put 170, that goes directly to that point on the rectifier output. So 170, about 170 volts, positive, comes through a 120K resistor. It gets filtered by this little 50 volt, 22 microfarad capacitor, which would happen to be that one, that little tiny one, that's right there. And there is a, I'm pretty sure it's like a Zener diode, because it's wired in parallel with this capacitor. And that, what that is doing is it gets an initial 170 volts. This is basically for you know, limiting the current here, and that goes straight into the VCC pin of the PFC controller. So that's taking 170 volts, clamping it down to some voltage, some lower voltage. I'm not even sure what it is. According to the data sheet, this thing has a maximum voltage input of 22 volts. I'm going to take a guess that maybe this is going to be about like 15 volt range or so. I don't know yet. We could actually apply power, and I think we should be able to measure that there. And as we can see, the ground is tied directly to ground. So this here provides the initial voltage to get the chip going, and you know, that begins the whole switching process to get this MOSFET, you know, boosting the voltage there. And you see this point right here where I have marked FB. I thought that this was like a feedback line for monitoring the output voltage. It turns out it's not, and we're gonna see that once I go over to the high voltage section there. So if there's no power getting to this pin here, or nothing like stable, you know, it's not going to do anything. The only other things we have over on this side over here is we have the high voltage input from the boosted output that goes through a couple of 750K resistors here. I'm guessing they probably did this to, you know, prevent like having one resistor taking the entirety of the voltage there. That would have had to have been like a 1.5 mega ohm resistor going straight down into here, into this inverting input on the PFC controller. That also has a capacitor right here down to this other pin here, which this it's according to the data sheet, it's an output of the error amplifier. I might show you a little picture of that here. I might just kind of stick it, I don't know, somewhere over here. So that there is for, according to the data sheet, a compensation network is placed between this pin and the inverting pin to achieve stability of the voltage control loop and ensure a high power factor and low THD. So that's what that's doing there. We can also see that up here we have the 170 volt input coming in, and this goes through a 1.5 mega ohm resistor, and that comes down to here, and then it goes into this mult pin, and that's the main input to the multiplier. According to the data sheet, this pin is connected to the rectified mains voltage via a resistor divider and provides the sinusoidal reference to the current loop. So that has some filtering and stuff going on down here, and there's a diode there, capacitor, and then a 10K, and that's all connected in parallel. And the only other thing we have here is basically this whole section here is a voltage divider. So that's our positive, that's our ground, and then we have like a voltage here. So this if this voltage fluctuates, you know, then the chip can kind of adjust for it. This other section here, that's also another resistor divider. As we can see, we got resistor here, and then just some stuff for like stability there. And already we can see that, you know, once we kind of break it down, even though it looks a little bit dense in here and like there's quite a few components, it's really not that complicated the way that this thing works. It's just, you know, a couple voltage dividers here for measuring stuff in the input. It's got its supply voltage, and then it's switching output. So yeah. So up to this point, we're at about right in this area, I believe. Like, okay, like say if we were to cut this like at this point, that's kind of where we are in the schematic diagram. So now let's jump over to this end here, which happens to be this area of the board right here, and that is this inductor. So this inductor is actually very similar to the common mode choke that's on the input here, with one slight difference. As we can see, at the input of the mains here, we have, you know, two coils that go, or two windings in this choke here, and that gets rectified. On this inductor, for the high voltage boosted output, we also have two windings, but one of them is center tapped. So I'm not exactly sure what, you know, maybe there was like some other use for this particular inductor that they decided to center tap it, but other than that, the two windings appear to be pretty identical. There are two diodes that are wired back to back at the two ends of one of the windings, the center tapped winding, and that would be these two diodes. There's this kind of large one here, and then there's a smaller one right there. And I am not entirely sure what the purpose of those two is, to be honest. Maybe they're doing some sort of clamping, because it is on the high voltage side. And that's like pretty much my only guess. I don't know the, like I said, it's kind of hard to read because there's like still some tar on that. So I don't know the actual values of these. Maybe we'll, like, if I can, you know, get us to do something, maybe I'll remove them after the fact or whatever, and you can see what they're supposed to be. Alright, so after the inductors here, then we have a big capacitor here. It's a 400 volt, 1.5 microfarad, which happens to be that guy right there. So it's kind of off to the side, but that's where the output goes. If you notice here, I have written 360 plus 360, like up at this point. Up here I have written plus 360F, so that's like the filtered output. So from this point on is where we power the big inverter down here for the lamps. Yeah, I say big, I mean it's actually kind of small, but it's just like, it's a really high voltage output there. And as I mentioned, there's a center tap here coming from the two big electrolytics. So that goes down and into the beginning of the windings on the output transformer. And let me zoom out a bit here so we can get a better shot of all that there. Alright, there we go. So that output transformer is this guy right here. It's fairly large compared to some of the other stuff in the rest of this ballast. And this guy actually has quite a few windings in it. And I've already like ohmed everything out basically. There are no broken windings in any of these inductors. Like everything checks out. Okay, so there is no problem with the inductors. On the diagram here, it looks like this is one coil and that is just center tapped. The reality of it is that there's actually two separate windings here. This is a high current winding, and the way we can tell is, I mean, it's going to be kind of hard to see there, but this particular point is that point up at the top, and it's got multiple strands of wire, and that's wound all the way over to this point. And as you can see, there's a little strand of wire coming up in that direction there. So what we have is we have a high current winding, and then we have a feedback winding, but they're both tied together at this point. That point goes to the point in between the emitter of one of the transistors and the collector of the other transistors, and both of these transistors are identical. Those are BUF 742. They're high voltage switching transistors, NPN. So basically what's happening is we've got our center point there, and we are switching between the positive and the negative at this point here. So that's basically getting the transformer, you know, kind of going back and forth there to oscillate, to generate our high voltage output. And as I mentioned, this is our one of our feedbacks to switch the transistors on and off. So as we can see, this one here runs over to here and up to the base of this top transistor here that's connected to the filtered high voltage. That's going through it's got a diode here, and it's got a resistor, an 82 ohm resistor. So when this pulse coming out of here becomes positive, that allows this transistor to turn on. It allows 360 or so odd volts to be passed through to this point here. That will, you know, turn the magnetic field going in one direction. When that happens, the other one gets basically a positive pulse here, and then this one becomes negative. So it's just going back and forth. That as best as I can explain it. That's what these two windings here are doing. So basically this winding is the same as this winding, but this winding is for driving the lower transistor, and that one is for driving the upper transistor. As you can see, the circuits are pretty much identical to both of them, except for the fact that this one at the base, and I didn't leave enough room because I didn't realize this was here, it's also got a diac right there at this point. So, and that's got a capacitor here to ground. That also runs up to here through a 1 mega ohm resistor to that center point there. And then this capacitor here, I think it might be doing like a dual purpose here. And one, I think it's part of a tank circuit here between this inductor. Well, this capacitor and the inductor, you know, would make like a tank circuit. But also I think it's being used to initiate the oscillations in this circuit. And I say that because when this thing first powers up and there are, you know, this whole area here kind of charges up, we're going to get a positive voltage, I mean with reference to ground over here, we're going to get a positive voltage flowing. It's going to go straight through this capacitor because it's basically going to be like a short. It's going to go through this 1 mega ohm resistor down to here, and as it approaches a certain voltage, you know, this is going to conduct, and it's going to allow this transistor here to turn on. And the reason why I think that this is the first one to switch on is because this was the one that's sitting with reference directly to ground, and these are NPN transistors. I don't think this is the one that turns on initially, because at that point in time, basically, like, you know, this is all kind of positive over here, so this doesn't have like a reference directly to ground in any sort of way. However, if I am wrong about this, you know, feel free to correct me, like leave it down in the comments below or whatever. I'm not claiming to be an expert on these sorts of circuits or anything, so yeah, if I am wrong about that, please do correct me. But as best as I can tell, I think that's how this circuit is working. So this powers up. It allows ground, you know, to be switched directly to the collector over here, which in turn provides a ground over to this coil, which, you know, basically starts the whole oscillation process, and then, you know, the transistors take turns switching like on and off. So after, you know, that applies power, then this side becomes positive, and, you know, flip-flops like back and forth. And I think this here, this diac is probably to keep the switching, you know, so it only happens like at a certain point in the, you know, once the voltage reaches a certain point, then the other transistor turns on. So there's no kind of like in between where both of them are on, and, you know, they're going to be like drawing high amounts of current, and then, you know, they end up burning out. So that's that portion of the circuit there. The output is really not complex at all. It's just one winding inside that transformer that goes to 4 capacitors, which we already saw here. So there's our 4 capacitors, and the output to those, one for each lamp. It just goes straight out. And the other winding that comes out of here, which is the yellow wires, those go like straight out to the lamps. They only provide 2, I think, for convenience, but in reality, you know, it's just like one line coming in and going out to everything. And in a regular fluorescent lamp like this, you know, like say this was the lamp here, I just kind of shortened it here, that this is not a resistor. This is just supposed to be like the end of the lamp. I just, you know, say that it's supposed to continue. This is technically supposed to be glass, but I just realized that now it looks like a resistor, and it's not. So we have 2 wires or 2 terminals at the end of each lamp, and that, you know, goes to a filament. The way this circuit works is it works more like a CCFL, you know, that you would find in like a smaller lamp, like say something, you know, you like put in a PC or something for like lighting. Well, or we used to. Nowadays it's all LEDs and RGB LEDs. Back when it first started, we used to put CCFLs in our PCs. Kids, get off my lawn, you know, all that. So basically this entire filament here is acting as one electrode on this end, and then the other filament on the other side would be acting as another electrode. So we just have a high voltage conducting in there, you know, and causing the lamp to glow. We are not directly heating the filament to start the lamp like we do in, say, one of the magnetic ballasted lamp, you know, fixtures and all that stuff. So, you know, with this, technically the lamp should last a lot longer because we're not constantly stressing out the filament. One last thing over on this section of the circuit. There is one winding that is kind of separate from everything else. This winding goes through a diode. It goes through a resistor, which I've pretty much determined to be a 10K resistor. And that is this set of components right here. This little diode and that resistor. One end goes to ground, but it's not the ground that's here. This is the filtered side of the ground, which we saw at this point right here. So we have our filtered 360 volts, and we have our filtered ground. I probably should have done something else to differentiate between the two, but that's what I came up with right at the moment. Okay, so this ground basically ties to the ground over on the other side of the circuit. The output of this I have labeled FB because I thought this was a feedback of sorts, and it's not. What I'm pretty sure that this is doing over here is once the circuit starts operating, it is used to power the PFC chip directly. That way we are not using this resistor as a current limiter and wasting a lot of power, you know, through that resistor there, you know, to have to be rectified. So the output transformer is actually also being used to power the PFC section. This diode here, you know, may still be regulating the voltage, but at least this resistor is not taking the load of doing the work of limiting the current. That resistor happens to be this resistor right here, and as we can see, it's pretty chunky because basically it's going to be dissipating quite a bit of heat. So what they're trying to do, from best as I can tell, is that they're taking the load off that resistor and making it so that it's operates a little more efficiently, and it doesn't rely on, you know, having to dissipate a lot of heat to power that chip there. So I mentioned a little earlier that I thought that maybe this had something to do with why this ballast doesn't work. Well, the reason I think that, this resistor is cracked. And I'm not sure if that was my doing when I was taking the ballast apart, or if it cracked at some other point in time. But what we can do is we can try replacing it. I don't have an exact resistor like this, but I do have like a, you know, like a regular 10K that I could stick in here, and we can try and see if it gets it going. So this is the only obvious problem that I found in the entire ballast. There are no other burnt resistors or damaged looking components except for some of the, or some, or one or more, I'm not sure, of the pins on one of these transistors was broken. Actually on this MOSFET over here, one of the pins kind of cracked, but I'm not entirely sure if that was also my doing from, you know, manipulating this thing around. They, like I said, these are kind of like flapping around, so it's really easy to break those, and that could have happened, you know, while I was messing around with this and kind of moving stuff around. That might have cracked, but it's only cracked from where it's soldered down here at the board. So the rest of the pins are actually completely intact, so I could just solder that to there and see if it does anything. One other thing that I noticed on this board is that even though it's like a single-sided load, they actually plated all the way through. So every single point on this board is actually a via and is plated all the way through. So that's actually pretty surprising, and it's, you know, it's meant to be fairly reliable as far as I can tell. If it was only, you know, soldered at the bottom, there was nothing to go through, then, you know, these would be like pretty weak, susceptible to cracking and stuff. But they actually did a pretty good job, in my opinion, with doing that. And, you know, so the solder like comes all the way up, and the pin is soldered, you know, basically on both sides. So that would be pretty good contacts there on pretty much everything. Whoa, this got messy fast. So I've been messing with this thing for a while now, trying to see if I could get it to do something other than, you know, just stepping up the voltage from the mains. But I can't get it to fire up at all. At one point I did get some flickering from the lamp. It was like kind of like ticking just briefly there, like a few times a second, but it would not completely fire up, and I'm not even sure how I even got it to do that. After a few seconds of doing that, something let out a little like delicate wisp of smoke, and it ended up being this thing right here. And this is one of the diodes. It's actually diode, the one that was up here in this section that I had kind of mentioned that I wasn't sure exactly what was going on. Well, it turns out that diode right there, it's a peak 6KE 200A, and what that is, it's a TVS, or a transient voltage suppressor diode. So I think what's happening there is like any transients from this section here are allowed to go through that diode, and then because this one over here is like forward biased, you know, it kind of goes back into the high voltage section of the power supply. So I'm pretty sure that's what that's doing there. That way it kind of like bypasses the choke, and it just goes straight across. So I think that explains that, although if I am wrong about that, anybody feel free to correct me. Other things, since I was like removing stuff and testing it, and I could not find like a single bad component in the circuit at all. I even tested the diex here with the oscilloscope, and I was able to, yeah, I mean, you can kind of see how there's kind of like a flat spot in between, like where the voltage is rising and before it like triggers, it's a little flat. And so they seem to be operating just fine. I checked a bunch of the diodes here, I pulled them out of circuit, I tested them out of circuit, and I can't find like any problems. So I don't know if maybe the transistors I used are just not adequate. I mean, that's could be very likely, that even though they're kind of similar, but they're not really designed for this particular purpose. And I think that could be what's going on, that yeah, it's just not working. Because yeah, over here, like I pulled out a bunch of other components, and while I was at it, I kind of filled in a bunch of the stuff that was missing, a bunch of information. I can't find any bad capacitors, like nothing seems shorted, although if they're leaky, I really don't know. There could be, you know, something that's kind of bad there. So pretty much like the only other thing I can show you is how I believe that this the PFC chip here is kind of working. So as I mentioned over here earlier, when this the mains gets powered up and there's the voltage present at this point over here after it gets rectified, it charges through that resistor there, the 120k resistor, and this capacitor here takes a little bit to charge up, and once this the input there at the VCC hits a certain voltage, this circuit starts oscillating, or it starts switching the MOSFET over here, and that's when the voltage starts getting stepped up. So I can at least show you that. What I've done here is I have two probes. I have one probe sitting at the positive right here of this capacitor, which is actually the VCC input of the PFC chip, and I have the other probe sitting at the input to the gate on the MOSFET there. So we're going to see how when this voltage rises, when it finally hits a voltage that this chip can start operating at, it starts switching that MOSFET, but after a little length of time, because this is switching and it's triggering the MOSFET, the voltage kind of drops, and then it just completely cuts off for a minute, or I mean it's like fractions of a second, but it just cuts off for a little bit until this voltage is able to rise up again and start triggering the MOSFET. So basically what's supposed to happen is at that period of time, when this starts switching, this voltage rises, this starts firing, it starts, you know, doing its thing. This winding of the transformer starts outputting some voltage, and then it takes over in powering up the PFC circuit. So that's what keeps the circuit running. And I mean, this happens in like a fraction of a second. I'm actually using like these exact same ballasts here in my garage, but they're kind of in fixtures and stuff, so it wouldn't be all that easy for me to get them down here and, you know, and start poking around with this stuff. I mean, they're fast. Like, you hit that switch like less than half a second later, the lights are like fully on. They do not take very long at all to fully power up. So, well, anyways, let me show you what goes on right here. So I've got these two multimeters. I've got the good one here, the Agile, and then I got the other crappier one. This one here is wired across the bottom capacitor right here. So I got the negative of that multimeter hooked up to the negative of this rail, and then I've got the positive hooked up to the center point, and then on the Agilent I have the negative hooked up to the center point, and I have the positive hooked up to the positive rail up here. So we're gonna see how the voltage kind of rises there. I have this one here set to 300, to a range of 300. This one set to 200. This one goes over 200, but this one will not go over 200. And I think that has something to do with the fact that I believe the negative side is the one that's supposed to be causing this thing to start switching. So I think there might be like a little bit of current going through here through the diac, and that's kind of what makes it, that side, be a little bit lower, because the positive side, unless it's getting switched through this transistor here, it doesn't really go to anything else. Oh, and also another thing that I had kind of missed is when I was taking it apart, I realized that there's a diode right here that goes to the center point of that totem pole there with the transistors, and then the other side kind of goes through to the other side of that diac there to this capacitor, across the back to the positive side through that, well, not to the positive side, but to the bottom side here of this winding through that 1 mega ohm resistor. But that's like the only thing that I had missed there. Everything else seems to be correct. Another thing I've done here is that I've actually hooked this up to an isolation transformer, because you do not want to be hooking up stuff that's connected directly to mains through your oscilloscope, because the ground terminal is, you know, completely grounded to mains ground. So I'm going through that isolation transformer there. That way this circuit here is completely isolated from everything else that has to do with the oscilloscope, so I can, like, you know, safely probe around on it. I have the ground lead connected to the negative rail over here. That's going to be like our ground reference for, like, you know, pretty much everything that's going on over here. So let's take a quick look at that, because that's at least something I can show you. So it's all set up. I've got 5 volts per division on each one here, and I will go ahead and switch it on. We're going to see the voltage rise on both of these here. Remember, the positive and negative rail. taken from the center point. So as we can see right here, and if I were to, let me see, switch the scale down here a bit, you can see that there is a ripple, and that ripple is the one that's present at this point right here. So we can see that this capacitor is charging, and once it finally reaches a point there, so let's see, I had it down to here, so it's about 5, 10, it seems to be about 11 or 12 volts or so right there. When it finally reaches that point, the MOSFET starts switching, and because the MOSFET starts switching, it drops that voltage, and once that voltage drops to a certain point, it stops the switching process until it's able to charge up again. And then, so basically there, it's trying to trigger the other circuit to start oscillating this section, but since this section is not working, then this kind of quits because it can't keep going, and that's when it stops. So yeah, nothing going on. But as we can see on the positive rail here, we have 200. Actually, that's like really high. I'm gonna turn this off because I think those capacitors were rated for like 250 or something. Okay, that was weird. And as we can see, the negative side here, it went up quite a bit, but now it's like dropping like super fast. So yeah, I really wish I could have done more, but I'm really kind of tired of wasting time on this here, and I haven't been able to get it to do much, so I'm not gonna spend more time on it. I hope that at least what I presented here was like, you know, fairly packed with information as to like how these things work. Like I mentioned before, I also was not expecting to do a repair on this. It just kind of got the best of me, which this stuff like tends to do. I tend to get like a little too much into it. Like I want to get it working because I just want to know like what failed, and it, you know, it doesn't seem like we really found out exactly what failed, although I think maybe like one of these transistors may have shorted at some point. And I guess there was something wrong with that TVS because, like I said, it started smoking, and I don't see any other reason why that would have started smoking unless there was like something really bad going on over here. Oh yeah, one other little thing. The resistor that was over here, the one that was cracked, it had colors of brown, black, black, red, red. And if that was the original values of, you know, like a 5-band resistor, that would have been like a 2%, like 10K resistor. And that seems really odd for something like that, for especially being like, you know, part of the circuit that powers the PFC. So I think it most likely was that it was supposed to be red, red, black, black, brown, and that would have been a 1% 220 ohm resistor, which I think makes a lot more sense than having a 10K resistor in that spot right here. I don't have a 10K or a 220, but I put in two 120s in series here, so it's about like 240. Which, I mean, it wasn't too far off, and it seems kind of, I don't know, it seems a little weird that they would have used a 1% resistor in that particular part of the circuit, because it doesn't seem like it needs to be anything like really critical for powering up the PFC chip. But, nah, I mean, I don't know. Whatever, maybe it was just something that they already kind of had in their bill of materials or something, so they just went with that. Yeah, I don't know. So anyways, I kind of want to get to some other stuff, so I'm just going to stop with this thing here. I think I've already wasted enough time on it. So I'm kind of happy to be moving on, because in the next video, I am going to be unboxing this. And nope, it's not actually a PhotoSmart 8450 like it says in the box there. It's something else that I think is going to be pretty cool, so I'm kind of really happy to finally be able to get around to this. So thanks for watching, and I'll see you guys around the bench.